You can use that to disagree. You can use that to indicate all sorts of things, that you're thinking something's happy or funny. So please feel free to use that little icon up there at the very top menu item. Again, it looks like somebody is raising their hand in the icon. And feel free to play with it a little bit. Also, feel free to type in questions in the chat box. We're not going to give everyone the microphone simply because when there's this many people, it can become difficult to hear everyone at the same time. But do feel free to type things in. And if anyone has any difficulties understanding things or any technical problems during the webinar, you can send a private message to Brian Russell or to Carlene Barbas. To do this, you just put your cursor over their names under the attendees list. You can see the attendees list over there, and you see a bunch of names. And if you put your cursor right over Brian or Colleen's name, you can click on private chat. It's a little pop-up and send a message directly to them. And it is time to get started. Welcome, everyone. We are so delighted to have all of you with us here today. My name is Christine Shupla, and I'm at the Lunar and Planetary Institute with Andy Shaner. We have a program called Explore that's geared for libraries with lots of different materials and activities for librarians. And so today, Mr. Andy Shaner is going to be sharing Marvel Moon with you, a variety of activities and ideas that you can use in your own institution. If you have any questions or problems, please do type them into the chat box, and we will try to address them. If you have any problems, again, technical problems, click on Brian's name or Colleen's name over there under the attendees list up in the upper right, and do a private chat with them, and they'll attempt to help you with any technical issues. And we're delighted to have you here. There was someone I spoke to earlier who was under the misimpression that this next hour is like a video for kids. This next hour is all about the program. So if you've got kids with you, they may get a little bored because we're going to be talking about the activities rather than doing them right now. And with no further ado, let me present to you Mr. Andy Shaner.
Thank you, Christine, and thank you all for joining us today. This is great to kind of see you out there. I am also an education specialist here at LPI, Lunar and Planetary Institute, with Christine in Houston. And like she said, we're going to talk about a program called Explore Marvel Moon. Now, Marvel Moon is one module within a larger collection under what we call the Explore program. The Explore program began about 15 years ago. With some librarians in Louisiana that asked LPI to help them bring space science, particularly NASA space science and exploration, into their libraries in an accessible way to their audiences. And it's something that hadn't really been done before, so they decided to take it on and see what they could do, and it's been really successful ever since. The Marvel Moon module in particular is, as you can imagine, about the moon. And it uses a comic book kind of theme. As you can see, these characters on top, and I'll mention more about them in a second. And what we're going to talk about today are activities that get across the idea of how the moon was formed and how, at least our current understanding of how the moon was formed and how it has evolved or changed since that time. A few more things about Explore itself is that one of the purposes was to create and distribute hands-on activities that are fun, designed for out-of-school settings like libraries, specifically libraries, rely on inexpensive materials. In fact, whenever we do these, we do workshops about these with librarians, we get everything at Walmart, and they're flexible. So you can either do each activity on its own, or you can use them all as one large module. You don't have to do one to do the other. They highlight Earth and space science and engineering concepts throughout different types of investigations or demos, crafts, and just conversations. We have provided training to children's and youth librarians in the past, as well as other community educators. More recently, we've started working with the American Camp Association. And it's primarily been funded by the National Science Foundation and NASA throughout the years. I guess I could have gone to that slide, but all right, let's go on to this one. So here's Marvel Moon. So if you go to our Explore website, you see the URL there at the top. And if you click on the hands-on activities link, which is here on the left, it'll bring up this menu below that of the different modules. And there you'll see Marvel Moon, the fourth one down. And this is the home page to Marvel Moon. This particular module was funded by the NASA Lunar Science Institute. That was a recent institute within NASA. So if you look there across the top of the web page, there's the welcome screen, there's a link for activities, background information. So the activities are all the different activities contained within the module, some of which we'll see today. Background is the background information. It's more about the science that gets presented with these particular activities. Resources include PowerPoints that have been given during past webinars or during live presentations for this particular module. So there's lots that you can find through here. There are hands-on activities, resources, which include books and websites and games and videos. Again, the background, the facilitator background information. Under resources, there's also links to archived online trainings that we've done with this in the past. Another option that we don't see right here is there's also a listserv for Explore. And if you would be interested in joining that listserv, you can send me an email and let you know. We'll get you that email either today in the chat box or make sure it goes out in a follow-up email from ALA. So first, also I want to take a moment and just thank ALA for doing this webinar with us today, hosting it with us, so we can get the word out to more librarians about this program. Okay, so Marvel Moon, like I said, kind of has this backdrop of a comic book, which is really neat. All the characters that you see there, they are all based off of actual NASA lunar scientists that all do different types of research related to the moon. And some of them do asteroid research as well, but we're looking specifically at the moon with this module. Okay, so here's the moon that we look at when we look up at the sky. It doesn't look exactly like that because this is a picture taken by a spacecraft, but it more or less looks like this with our eyes. We see these large dark spots and then lighter areas, kind of the two colors we see when we look at the moon. But it hasn't always looked this way. It has to us. It doesn't really seem to change to us, but when you look at the geologic time or history of the solar system, the moon has not looked like this. And that's what we're going to talk about today. Is we're going to talk a little bit about the science of how it's changed from how it formed and how it's changed since then, and more about the activities that will help illustrate these concepts in an engaging way to kids in library programs. So just real quickly, when we look at the moon, we see these dark regions, which we call maria. We'll talk about how those formed. The darkness is more or less it's a volcanic rock that's solidified, and those are lower in terms of elevation compared to the brighter areas, which we call highlands, and we'll talk about differences between those two things other than their elevation. Highlands are also the oldest parts of the moon, and the maria are younger, relatively younger. I'm not going to say they're young, but they are younger. All right, so the activities that we're going to start looking through are activities. And the first one is called Wham Moon. And this is an activity that gets at our current understanding, or our best understanding of how we think the moon came to be, why it exists in the first place. So I have a real quick question maybe you might want to reply to in the chat box is, has anybody heard of any ideas of how the moon formed? There have actually been a few that have been proposed over time, but there's been one that has risen to the top, and the other ones we've been able to discount quite simply, actually. But has anybody heard of any ideas of how the moon formed? And just put that in the chat box. Let's see what have you heard?
And we'll give a couple seconds here. It looks like a couple of you are typing, so please, some more of you, feel free to enter your thoughts. What did you learn when you were in school? What have you heard from your friends, from scientists, from books? And it looks like Eric has written down that it formed when a meteor slammed into the Earth and broke off a chunk, and by the rotation from the Earth, the moon pieces formed together. And John Dees wrote that a large asteroid impacted Earth and the moon formed from the debris.
Okay, so both of these are great, actually pretty descriptive, and they all basically involve some big thing hitting the Earth from somewhere else out there in the solar system. That is one idea. In fact, it is the leading idea that we're going to talk about, that we will also model with the activity. The other ones are that have in the past are interesting, but like I said, they have all been discredited. Okay, so back when the Earth first formed, you see it in this image on the slide. It looked very different than it does today. About 4.5 billion years ago, it was mostly completely covered in molten lava. Looks nothing like it does today. Would not be a place anything would be able to survive on. And it was at this time that, as Erica and John mentioned, there was a large object that had formed somewhere else in the solar system. Its path, as well as Earth's path, they crossed, and there was a bit of a cataclysmic result of that. Now, this object, it wasn't Mars, but it was an object about the size of Mars, but not Mars itself. It hit the Earth, but it hit it in kind of a glancing blow. It wasn't straight on, it wasn't dead on, right down the middle. It was more of a glancing blow. But we believe that this collision took place at a speed of about 25,000 miles per hour, and it took about 10 minutes for this collision to take place. But what this did is this threw off debris that wound up going into orbit around the Earth. What remained of the smaller object actually kind of went into the Earth and was folded into the Earth. But debris from that impactor and from the Earth wound up going into orbit around the Earth. And that's what these two illustrations are showing on the left. Initially, there was a lot of debris out there in several large pieces, but by the time everything was said and done, there was one moon that was orbiting the Earth, made up of pieces of this original impactor and the Earth as well. So what you can do with this activity is do what we did. We can ask the children, what are their ideas on how the moon formed? Where did it come from? And then give them some Play-Doh and have them reconstruct their idea with Play-Doh. And then you can introduce what the current understanding is. It's something we call the giant impact hypothesis. And there's more about that in that background facilitator reading. These are two screenshots from a webinar we've done in the past. On the left, there's a blue Earth with an orange. The object actually was called Thea that came in to hit the Earth, and you bring it in. You show how it's a glancing collision. And then you tear off pieces of the Earth and that impactor, and you fold the rest of the impactor into the Earth. And then you're left with these debris that are orbiting the Earth, and there you see the Earth with the impactor has been more or less swallowed into the Earth. And then when you're done, and all that debris is orbiting the Earth, and eventually it comes back together to form the moon, you see this object that's about a quarter the diameter of the Earth, and is composed of both the orange and the red, or sorry, orange and the blue, to show that it's a result of both objects. And here's the first, this is part of the activity for the write-up. This is comic book that goes through those steps in about 4 panels of what happened to form the Earth. And then they're in that, on the bottom in the middle, kids can draw what the final product was of this collision. And there we see a statement by one of our scientists, superheroes, if you will, part of the Marvel Moon team. Now, one result of this impact in the formation of the moon is that both the Earth and the moon have layers on their interiors. It's not just a solid one piece of thing in the middle. There's these different layers. So In the chat box, can you what are some names of the Earth's layers that you may have heard? Maybe you didn't know the Earth had layers, but if you've heard that before, what are some names that you've heard um, attribute to the different layers of the Earth? I can kind of help you. There's an outer part of the Earth that we live on that has a name. There's a very center, and then there's a layer outside of that, and a layer kind of in the middle of all of that. Crust and core. Okay, that's right. We have the crust is the outer part that we live and build things on. The core is in the middle, a mantle. Okay, and that's below the crust. That's the next one down. Mantle. Okay, good. So you've heard some of these out there. These ideas out there. Great. Well, it turned out the moon does too, has layers, but not as many. It's not as complicated as the Earth is. And that brings us to our next activity, which models the interior of the Earth and the moon. And this is a fun and a tasty one. So if we just start here by looking at the Earth and the moon, okay, on the outside, they look very different. The moon's just different shades of gray, and the Earth has lots of different colors. And just to point out that these are not to scale. The moon is actually a quarter of the diameter of the Earth, so you could line up 4 moons across the equator of the Earth, in other words. But it is smaller, and this is more just to get the point across. They look very different on the outside, and they're also different on the inside. So if you want to make a model of the Earth to show what it looks like on the interior, and if you want to use food to do this, here's the recipe to do that. As you can see, it uses 4 3/4 Rice Krispie treats. Uses some red icing, green and blue sparkles, a donut hole, or a marshmallow, a larger but not a huge marshmallow. Certainly not the mini marshmallow. Some chocolate chips, and then you might want to use a ruler, a plastic knife will come in handy. Cardboard plate, of course, and always good idea to have some wet wipes or something nearby that you can clean off sticky fingers when you're done, because they're going to get sticky just making these things. Yes, Christine, there is a lot of sugar, and let me just tell you, when you get done with the Earth, I ate an Earth one time, and I was off the wall for a couple of hours, and I am not a small person. So just be aware of that. Recipe for the moon is a quarter of a Rice Krispie treat, so you're going to actually have 5 in total, but you're only going to use 1/4 of a Rice Krispie treat for the moon. And you can see similar things: the cinnamon candy, hot cocoa mix, powdered sugar. That'll help give you that color of the outside of the moon, and some chocolate chips, and again, similar things. Now, if you go through this, it'll also explain how to make it. You need how to put everything together. But once you do get everything together, here's what an Earth could look like. You're going to have like the blue represent the oceans, and you'll have some Rice Krispie treats you put on the outside to be like continents that are above the ocean. You can stick the chocolate chips in them to represent mountains or volcanoes. And then you cut through that, and you reveal what the interior looks like, and you'll see this from the instructions. But there you'll see the outer part. Get the ruler here. You'll see the outer parts here with the different crust. The different sprinkles represent the oceanic and continental crust. The Rice Krispie treat itself represents the mantle. And there's a thinner layer of red icing that represents the outer core. And then that marshmallow or donut hole, whichever one you use, represents the inner core of the Earth. So there we see our Earth in layers. Now when we look at the moon, here it is. It's a little bit smaller. It has that brownish looking grayish crust that we get from the cocoa powder and powdered sugar. There you can press a couple of chocolate chips in it upside down to make it look like the big basins, the big dark mare on the moon. When you cut that in half, which is a little bit harder to do, especially with that red hot in there, you see that the red hot in the middle represents the core. And there is no outer core, so it goes right back to a mantle represented by the Rice Krispie treat. And then the crust, in this case on the moon, is represented by the cocoa powder and the powdered sugar. And when they get all done with that, they can use this page in their comic book to draw the layers of the Earth and the moon and label those. Okay, so the Earth and the Moon wound up having layers after all was said and done with this collision, but how? How do they get layers? How does that happen? That's a whole other question in itself. And this next activity called moon mix gets at that, illustrates that. You notice we call it infant moon because at this stage in the moon's development or evolution, it was still what we might consider an infant. It was young, and this all happened at the very beginning. So this illustrates, this figure just points out that the moon has 3 layers, has a core, a mantle, and a crust, versus the 4 the Earth has. The only thing the moon's missing the Earth has is the outer core. Um, so the early moon, after it formed, was very hot from that collision. And what happened was there were different minerals that were forming inside the moon as it was cooling off. And some of those minerals were dense, and some of those were less dense. And the really dense ones, like iron, all sunk to the middle, and the lighter ones all floated up towards the top. So basically you have this separation of layers because different minerals that made up those layers are at different densities that were able to sink or float in this magma that the moon was made up at the beginning. So to illustrate this, we need something to contain our minerals, so to speak. And with that, we have you can use a plastic bottle. You can use like a 16 ounce or just one of these smaller ones to use to contain everything. And then you need something to represent the minerals, or will wind up kind of representing the layers actually within the moon. So you need different objects that will float and some things that will sink. And it also depends on what fluid you use. But our example here, we have some styrofoam, peanuts, buttons, aquarium gravel, beads, wooden beads, maybe some beans, and this is like confetti, plastic confetti kind of stuff. So all different kind of things that will sink or that will float. In this example, we've got a pan. For the interior, you can use, for the liquid, you can use pancake syrup or vegetable oil or corn syrup. You can even use water. But for the moon, we've got 3 different layers: a core, a mantle, and a crust. So the mantle could actually be represented by your liquid, and so then you just need to come up with two other materials, one that will sink and one that will float. And the end result could look something like this. This is one we made that I think we used vegetable oil, and aquarium gravel, and I think beans. And the thicker the material, like the corn oil or the vegetable oil, for example, the thicker that is, the longer it takes these things to separate out. If you use water, it's pretty quick. But if you use something a little more viscous, a little more thick, it'll take time. So you don't want it so thick that it's really hard to mix them up to begin with, but you want it thick enough that it doesn't just correct itself really quickly. It's a really fun activity. And again, with every activity, there's a comic book page to this. So in this activity, what you would have them do actually is predict. You have some materials and ask them which ones they think will float, which ones do they think would sink, and they can check off which ones they were right about.
Andy, we have a question. Can you use a combination of water and corn oil?
Well, I'm assuming those two aren't going to mix.
Correct.
So the water, I'm assuming, would be the one that would float.
No.
No, the corn
oil will float.
The corn oil will float. So you could do that. They won't mix together, but you could use it as layers. So if you could think of a third one that's even more dense than water.
Or lighter than the corn oil. You could use the water for your core, and you could use the corn oil for your mantle, and find something. See if straw pieces or something else will float on top of the corn oil.
All kinds of possibilities that you can do with this. Try it. Just trial and error. It's fun just to see what you can.
That's the fun part for the kids too, is letting them try out which things will work.
It's a good question. All right, that takes us on to our next activity, where the moon's grown up a little bit. It's now a kid, and we call it Kid Moon, and this is Splat. And at this point in the moon's history, it has formed. It is differentiated, it's separated out into these different layers, and the surface is solidified. We have a solid surface. And something interesting happened, we think. So that the moon formed roughly 4.5 or 4.5 billion years ago. And we think about 4.3, so about 200 million years later, there was a large amount of very large impacts that happened on the moon. Very big rocks that were still in the solar system, or that came from other parts of the solar system, probably the asteroid belt, just were bombarding the moon. And not just the moon, but the Earth as well. But this record is really well preserved on the moon. And it's something we call the late heavy bombardment. Basically, later on after the moon formed, more big rocks started hitting the moon. And they left their mark in these basins. We looked at that picture of the moon earlier. We see those big dark circles. Those are actually very, very large impact craters that were formed from these large asteroids that would have hit the moon during this time. Now, when those basins were created, they didn't become dark like that all of a sudden. Something else had to happen to give them that dark color, and we'll see what that is in a little bit. So to model this idea of the moon after it formed and after the crust solidifying, these huge impactors coming in and hitting it, it's a pretty fun activity. Probably best to be outside and in the summer when you're doing this. But you're basically making impactors out of water balloons, and you're going to see what the results are when you drop them. So a lot of times the water balloons don't come out perfectly round, and for the most part, that's actually true of most impactors. They're not perfectly round from the asteroid belt. But take a water balloon and fill it up to where you can fill it up as big as you want, as long as it doesn't break. But what you want to do is, as soon as you fill that water balloon up, you want to measure it, and just measure the short dimension. So as you see in this picture here, we measured along this dimension and not this one. So measure the short dimension this way, and in this case, this balloon was about 2.5 inches wide. Then we dropped it. We created this big splat here you see on the pavement. Very, very big, circular, and you can see little rays coming away from it in all directions. And there you see some pieces of the balloon left over. So we took this balloon that was 2.5 inches wide, dropped it, and it resulted in this splat. And when we measured just the circular part of that splat, it came out to about 44 inches wide. That's quite a bit bigger than the balloon itself. And this is something interesting to show you. Here on the left, there's a big impact basin on the moon called Orientale Basin. And here's the middle of it, and there's these concentric rings that go out from the center. This is a picture of Mars, Texas, superimposed on it, and that's to scale. That shows you how large that impact basin is compared to Texas.
Okay. We believe that ALA will be archiving this video chat. Yes, Erica, thank you. And Diana wanted to know how high you were when the balloon dropped there for the 44 inches. You were just standing about, well, Andy's a pretty tall guy, so I'm going to say that his hand was probably about 5 feet off the ground. But you can have the kids experiment dropping the balloons or even throwing the balloons. And Brian says, yes, this will be archived. And the link will be sent out to everyone on this tomorrow. So when you drop a balloon or throw it, the width of the splash is going to be proportional to the size of the balloon, and so that proportion is pretty interesting.
So perfect segue. So what you do is you take this page in the book, and down here at the bottom or at the top right corner it says impactor size. Here you write down that width of the balloon before you threw it. And down here where it says the crater size, that's where you write down the width of just the circular part of that splash. So then you take the crater width, which is the splash width in other words, and divide that by the impactor or balloon size, and you should get some number. Okay, and this is a ratio. And it turns out, in this case, our ratio was 17.6. So you take our splash width divided by our balloon width, and we got 17.6. And what's really cool about that is that falls within the range of what most scientists believe that impact craters are 10 to 20 times the size of the asteroid that created it to begin with. So that's a really cool result that you get with this. Now, there are some limitations to this model, meaning, is this model really accurate? Well, in one way it is in terms of the number that you get, this ratio. But one way it's not accurate is that you don't actually have a crater, right? An impact crater is a hole that gets excavated out of the ground. But you don't see, there's no hole, of course, you're dropping it on concrete. But the size, this ratio is the same. The balloon more or less gets destroyed, which is what happens in an actual impact event. So that's also accurate in what happens in these actual events. But the fact you don't get a crater, that's kind of disappointing. But there are other activities that you can use, that you can do, that will give you a crater, but it doesn't get rid of the impactor, and you don't get the same size. Okay, so moving on in the moon's history, we come to something called teen moon or moon ooze, and this illustrates the stage of the moon's evolution when it went through a lot of volcanic activity. Down there at the bottom of the screen, you'll note this says that this volcanism occurred after the impact, so after this idea we call the late heavy bombardment, and most of this volcanism occurred between 3 and 1 billion years ago. Now, we said it started about 3 billion years ago, and we say the late heavy bombardment ended 3.8 billion years ago. And in your mind, you might be thinking, okay, 3.8 versus 3 billion years ago. That doesn't really seem like a lot of time, but it really is. That 0.8 represents actually 800 million years. That's a long time. So there was 800 million years between the time that this bombardment ended and the volcanism started. Which tells us that, at least at that time, the moon's interior was still hot. It was hot enough to have magma under the surface. Now, what happened basically was the impacts from this late heavy bombardment weakened the crust. It didn't necessarily crack it, but it really weakened it. So you have this hot magma down below that wants to push its way up through the surface, and where it found areas that were weak enough, it was able to punch through the crust. And then this lava spilled out and it filled in these really large basins that have been formed during the late heavy bombardment. So it's not necessarily volcanism like we think of Mount St. Helens. It may be more a little like Hawaii. This lava is very runny compared to lava that you would see from Mount St. Helens. And they're just these big floodplains where lava just came up through these cracks and just filled it in. So here on the left, we see one of these big Mare Imbrium on the moon, one of those big circles on the moon. You can see it's circular from the crater impact that created it, but it's also lower, so this lava came in and filled it in. And over here on the right, we see these are different fronts from where lava stopped. There's different periods of volcanism, and these are the fronts where the lava ended as it solidified. And so moon ooze is the activity that illustrates this. And you start with two, in this case we have two plastic plates. It's just a small kind of dessert plates. So you have one that you don't do anything with. Another one that, they're kind of hard to see here, I admit. But right in here you might see some slits that we cut into the plate. Okay? And those are going to represent cracks that lava is going to come up through, or magma is going to come up through. And then we also drew in some circles to represent craters. Some craters within craters, or craters within craters within craters. So and we'll get to why we did that in a second. Okay. So then what you do is you need to get some magma. So in this case, we just took some water and we colored it with red food coloring, put it in a syringe and poured it in the plate. You can do whatever you want to put the water in the plate. That's just what we did. So you fill up that bottom plate with some red water, and that represents a magma chamber, or a chamber of magma that's underneath the surface that's trying to make its way up to the surface. Then you place that top plate on top of it, and as you start to press it down, that magma or that water comes up through those cracks that we purposely put in so that the magma could actually get out. And then as you press down more, depending on how much water you put in, it will completely fill up that top plate. And as you can see, it's not only coming in and filling in that basin. The top plate also represents one of these large basins that was formed. It's also covering up the craters that were already there. Now you can see them, of course, because that black magic marker is going to come through the water. It's not really going to hide. It's actually a pretty important idea when it comes to looking at the moon and looking at different surfaces across the moon.
So Andy, would this be done as a demonstration then, rather than having the kids do it themselves?
That probably be a little better. It could be kind of messy and kind of staining. I would say leave it up to you. And I mean, you know your audiences and your kids. You know what they could do and not do. Um, but I would at least start as a demo, and if they want to have, I'm sure they would want to try, especially if you introduce a syringe. I know it made me want to try it. So covering up these craters is very important. And what happens is when you have lava coming out and covering up these craters, the craters initially were on a surface of the moon, but when you bring lava up like that and you cover it up and you erase or cover those craters, you have created a new surface. And that's really important if you want to try to figure out how old a particular area on the moon is, which we'll get to actually with our next activity. But again, here is the comic book page from that activity, where they can draw the lava oozing up through the moon's surface, and then ask them a question. Where did the lava come from, and check which applies, where that lava come from on the moon. And all this information again is going to be in that background facilitator information for you. Okay, so I mentioned that it's important to see how lava can come up and fill in a basin and then cover up craters, which you can actually see in this picture on the bottom. You can see where some craters have been filled in, not completely, but almost. This one's almost got filled in, but not completely. But in the chat box, what do you notice a difference between these two images from the surface of the moon? What's one big difference that you see? Multiple attendees are typing. Excellent.
We'll give you a little bit of time here to finish typing your thoughts. You're comparing the images. And Erica's finished typing, but a couple more are still typing, so let's let them finish typing first. And the bottom one, Erica has added her thoughts that the bottom one seems to have been there longer with more lava coming up and filling the craters, perhaps. And Kay says the first one has protrusions, and the second two has holes. And there's an interesting thing, Andy, do you want to share about whether something looks like it's up or down, inverted? Because that's tricky. Andy, several people now, Trina and Sandy and Erica have said that the top one looks like it's boiling or bubbling mud, and the one on the bottom is smooth. It has some holes, but it might have been filled up by lava like you described. For the top one, do you want to describe for everybody how it formed? Please finish their thoughts, and we'll get back to what you were typing as well. Up at the top or B down at the bottom? Which one is older? We've gotten several good comments and feedback, and we're delighted for your feedback, frankly, and we'd love to hear from you what you think about this webcast, how we can make changes to them in the future. There were questions about the next one. Someone asked if it would be, would the activities for it be available, and will it also be archived? And yes, the next webcast will also be archived. Brian and Colleen, will people be able to access the archives of the next webcast if they aren't able to attend? And Kelly asks if we have programs for adults. Most of our material is for kids rather than for adults, but we do have a lecture series that we host here at the Lunar and Planetary Institute called Cosmic Exploration Speaker Series. If you're here in Houston, come by. It's free. If you're not, the past ones are recorded and available online for you to check out, and Andy's in charge of that as well. We've got another one coming in a couple weeks where we have speakers from all around the country come over here to LPI and give presentations. So, and we serve wine and cheese afterwards. Make it nice and fun. So, and Evian says he's going to try it at home. And Brian says that there will be an archive link for the webcasts. And okay. And folks, in case you missed it with all the texts and tweets, Brian had said that please, even if you can't be at the next webinar that we're going to be doing with ALA, please go ahead and register, because that way you'll be sent the link so that you can get a copy of it after the case. So if you can't make it but you still want to see the recording, register anyway. Tell your friends about it if you think that they'd enjoy it. We'd love to have them. March 10th, as Brian says, at 2 p.m. Central, and he has a link there where you can register. And Diana says she's already registered for it, so